Okay, everybody, we're going to do M&D chemicals now. There seem to be some problems with it as well, and I'm going to post this in the announcements when I'm through with it. Here it is, and I give you the text reference there, pages 54 through 59 out of the textbook, and starts over on page 54. We're right there, and this is a minimization problem. And we start to we're given the number of, we're given the variables here, the number of gallons of product A, and then product B. And then we see some some demand. I write the constraints for these demands for each product. And we're going to do a cost minimization. Here it is. And then we have our constraints. And the authors give us the graphical solution. And then they talk about surplus variables and handling them. And this is the solution from the web file, okay? This is using that little tool over there called Lingo, but to use it, it's about $150 more for you to pay for their lab, so I'm not going to do it. But let's look at this for just a minute. Here's the solution, the objective value. The cost minimum, with the minimum cost 800. Okay, this is the original data. We're going to make of that one type of chemical. We're going to make 250 units of it. Then we're going to make 100 units of the other, and we have some constraints, and these are discussed there in the text. And you can see the Lingo explanation is not that great. And then sometimes we have some alternative solutions. I'm going to open up the key. This key consists of, first of all, the student file from the Anderson text out of chapter 2, the M&D chemical. Okay, here's the key. Here we have the processing time for product A, and then the processing time for product B. Here's the total amount of time available, okay? And then here's the production costs for each. Here is the minimum amount we need to produce overall, okay? We've got to make 350 gallons of this stuff, I guess, or units. And we have to make at least 125 units of A. So when we talk about a minimization problem, we're saying there is a floor or baseline cost and or output level we have to achieve. Okay? Now here's the data model, and this is pulled out of the text. Of course, the student files, the Anderson, the student files, Chapter 2 would have M&D, and it's good to take a look at the text, pages 54 through 59, run you through that and end up with that logo solution we just saw, okay? And they give you the verbiage, okay? And you really will not make much sense unless you open up the data file and take a look as well. As it ends up with these constraints, we have these left-hand sides, and we're throwing a little bit of a curve here. Look at this. In this case, the processing time has to be less than or equal to 600 hours. Now, the demand for the product has to be equal to or greater than 125 units. We know the demand is 250. The total production is 350. And here's the processing time. Okay, so we have two minimums we're dealing with. First of all, we've got to make at least 125 units of product A. And secondly, we've got to produce everything we've got to produce 350 units of A and B, okay? And we only have 600 hours to do it. Well, let's look at the solver. Now click on data. Look over here to solver, and you'll see, here we see the objective function, which is B17. And in this case, we're going to minimize. Okay? And we're going to change these variables B16 and B15, B15 and B16. And then there's the constraints. B20 through B21 are equal to or greater than D20 through D21. The left-hand side and the right-hand side. But then this time in this minimization, okay, B22 has got to be equal to or less than D22. Before I run the solver, let's look back at this for a moment. Roll down. We saw our processing time has got to be less than or equal to this. So I'm going to go back to solver, okay? And I've got everything set up. I'm running a simplex LP, and I'm going to write solve. And there we've got the solution. Okay, and the minimum total cost is 800. Now I'm going to go ahead and get the answer report for the original. I can do that, and then get the sensitivity report for the original. Okay? So if I want those reports, I just click on here and generate them. I'm not that interested in these. So I'm just interested in, okay, here's the assignment. If the processing time is increased by 19% per product, and if the time available is decreased by 8%, let's go over and look at this in the solution area. And so I did a tab. All I did here is I took the original tab. This was out of the student files. I duplicated it, and then I put in the solution. And let's look at this. The processing time is increased by 19%. Product A, 2 times 1.19%. Over in the original, it was 2. Now in the solution, it's 2.38. Product B equals 1 times 1.19. I'm just having you change some variables. Folks, there's nothing all that terribly difficult about this if you just upload the file, if you get the file out of the student files and you change the variables and then just execute the solver. That's all you really have to do. What I really I've given you here are solution files out of the text, where the text shows you the solution, and then what I'm saying is, okay, let's change some of these variables to see what we get under different operating conditions. That's how we're going to learn and kind of understand. That's how we're going to learn and understand what we're doing here. Okay, so in this case, the processing time has gone up by 19%. Who knows why? It could be any one of a variety of reasons that we have to spend 19% more time processing it. Okay, so I'll go back over here to the solution. And then the production cost, nothing has happened there. However, you and I would both intuitively know that if it takes me more time to process product A, even if the production cost stays the same per unit, it's still going to cost me more. That's only common sense. In fact, the cost should go up, well, 19%. Look at it here for the original. This is on a per unit basis. It takes me 2 hours to make it. Product A. Okay? And the production cost is $2. Okay? Well, it's $4. Now I'm talking about $2.38 times 2.38 hours times $2. Time is money. The same story over here with product B. Okay? Now again, we have to stay within our production parameters. We still have to meet those minimums. We've got to make at least 350 units, and we've got to make at least 125 units of product A, even though we're facing a 19% increase in the time to process product A as well as product B. Then we have another kink thrown into this, and that is the time available is decreased by 8%. Now notice right here, okay, I had 600 hours originally, and I've reduced this by 8%. Now I could have done equals 600 times 0.92, and I'd get the same thing as 600 times 1 minus 0.08. Doesn't matter. It's still the same. It's 552 hours. So now I'm having to spend more time making this stuff, and I have less time to do it. And I'm maintaining my cost structures, and I'm maintaining my production constraints. This is a very real world problem. I'm literally being asked to do the same with less. That's why we call it a minimization problem. And you're going to run into these, whether it's budgeting the hours, maybe some division or department or company that you manage or own, whether it's materials or handling them, assembling them, or processing materials. This is they've got some kind of, they work with batch chemical processing here. You're going to run into these kinds of problems. That's why I keep saying this is so real world. Okay, this is a very common thing that people face. So why would it take more time to process this stuff? Well, it's pretty evident. Well, it's not. It can be any of a number of variety of things. It could be, for example, that the stuff our vendor has sent us is junk, or it's not very good. So I have to work with it more to get it to an acceptable level. Okay. It may be that that in my processing, I've had a machine go out, or my machine's not working as efficiently as it did, and I'm waiting on the replacement, and it's not here yet, but I still have to fill the order, on and on and on. Okay. Well, we've got this solution, so let's go back up here. We'll go to Solver. Now click on Data. Okay, here we are, and we have the objective functions, B17. And I'm going to minimize, and I'm changing the variables B15 and B16. That is the gallons produced. And then I've got my constraints, B20 to B21, equal to or greater than D20 to D20, and then we have that constraint, that Boolean operator that's going just the opposite direction here on B22 has got to be less than or equal to D22. Well, let's run the solver. Okay, and it tells me it can't find a feasible solution. Now I want to show you, okay, something very important that you might have run into or had a little bit of a problem with. As the book has talked about, okay, there are going to be some times when we can't find a feasible solution. There may be a range of feasible solutions, but we can't find a best solution. Okay, and the text, as it works you through some of that linear algebra, talks about it. The truth is, there are going to be some of those times when we are operating in what we would call a suboptimal level. This is one of them. Many of you, okay, I gave you credit and said, you know, you did a good job. The correct answer should be 898, not 892. Well, I just ran and got 892. So you're going, okay, well, Dr. Harmon, tell me, how'd you get 89? Well, because there's not a feasible solution, it's going to give me a range. So I'm just going to cancel this and watch what happens. I'm back to 898. So there are there's a range of suboptimal choices for me. And the one that most of you popped up with was 892. I ran it and got an 898. You say, well, why? Well, because since we don't have a true feasible bounded area, and if you've been reading the text like you ought to, this will make sense. If you're not, time to put your nose in the book, okay? When we talk about the feasible solution, if you look at those algebra, if you look at those graphs and they show you the area for the feasible solution, what that means is that anywhere in there, you can get a feasible, i.e. near optimal solution, but you'll have an optimal solution, excuse me. So that feasible range, those are fine, but if you want really the best one, here's the best answer. Well, when we work in suboptimal situations, as we are here, where we've changed the variables, okay, that doesn't look so good. But if you go back and you look at our original situation, the authors gave us this nice problem, okay, and I'll run Solver again for this tab. And note, I've got a solution. But my world goes haywire when I go over here and the boss comes and says, I'm sorry, we can't replace your machines. It's going to take it about 19% more time to process each gallon. Oh, by the way, we have a big job coming through, so we had to reduce the amount of time. We'd cut your time available by 8%. So you've got to spend more time per gallon with less total time. You say, that's absurd. Well, yes, but those are the situations in which you're going to find yourself at work. And a tool like Solver says, all right, I'm going to work with what's the best I can do with what I've got, okay? And I'm going to get some suboptimal solutions. So many of you got 892. I got an 898 when I ran this. So I put 892, close enough. 898, fine. And I can open the solver up here and I'll show you. That number just didn't come from nowhere. There it is. But now if I run the solve, watch. It'll give me the warning. Solver can't find a constraint at which can't find a point for which all constraints are satisfied. Something's got to give. And minimization problems and maximization problems and target values. So we try to work the best that we can. Okay, what I said with 892, yeah, I didn't take advice. 892 is close enough. I had 898 when I ran it. He says, is this like kind of random? Yes, because you're operating in a suboptimal world, you have some randomization at work. Okay, well, that's pretty much it, folks. And hopefully this will help you. I want you to take a look at this stuff, and this will be here for you Monday, and your questions, I think, are there for you to take a look at and go back and think about how you did it. There's some of you who posted and did a great job with both assignments. Some of you just simply put up, I'm not sure what you did, but that's okay. Yeah, and if you and so this is just a process of doing this the first time. Okay? Well, I will see you tomorrow and we'll do some work. Have a good one.